In this video, we're going to be going over page 5 of the notes on solving inequalities in one variable. Our first example, we have a function f of x equals, and I have it being the product of some different binomials. Now notice that these are linear. The first and last are linear, but the second one is a square binomial, quadratic binomial. So we want to find what kind of inputs are going to cause our output to be 0. What kind of inputs are going to cause our output to be positive values? What kind of input will cause our output to be negative? Now the first thing we're going to do is we're going to sketch a graph of this function f of x. So if I look at a graph, I know that I have zeros at -3 and 4 on the real number system. X squared plus 1 does have the ability to be 0. However, it's not going to show up on the real number system because I would require me to use -I and I. So on my graph, I basically am going to have at -3 a 0, and at 4 I'm going to have a 0. Now the function is going to be degree 2, 4, 5. And if it's degree 5 with a positive lead coefficient, if I multiplied this all out, I know my graph is going to start at -infinity. My x values are going to, as they increase, are going to cause my y value to increase. Now, this middle term of x squared plus 1 is going to cause some fluctuation of the graph. However, the graph is never going to dip down below the x-axis because I don't have any more zeros other than this value here. Now, there is an even multiplicity at the x value of 4. So there is going to be some curvature that is going to take place because of this being an x squared plus 1. I'm not terribly worried about what curvature is happening up here, but I do know that once this graph comes down, it's going to touch the x value of 4, and then it's going to go back up and have its typical cubic, odd degree polynomial type of a graph. Okay, so I just need to know what x values cause my function to have y values that are 0, which I know these are the 2. I want to know what kind of x values cause my y value to be positive, and I can see that's going to take place when we're up above this x-axis, and what type of x values cause my graph to have negative values. Now, technically, this point is a 0, and it's neither positive nor negative. So when I'm describing what kind of values I have for the x's that cause my y value to be positive, I would say -2 is less than x is less than 4, or when x is bigger than 4. Those are values that will cause my function to be positive. For negative, I can see that anytime I have an x value that is less than -3, my y coordinate or my f of x value is going to end up being negative. So when x is less than -3. So when we look at a function and it's in a factored form and we want to identify where is the graph have zeros, where is it positive, where is it negative, this is a technique of graphing and then identifying those spots is a very important process to be able to use. If this graph had been a velocity graph, these points at 0 would be where my object was at rest. If, again, this is a velocity graph, when my graph has positive values, these x-coordinates would describe the times in which I would be moving in the positive direction, and these, where x is negative, would be times where my object was moving in the negative direction. Okay, now let's look at a little bit more complicated question. Now this type of analysis, if I have 2x cubed minus the following part of the polynomial, I want to know where this graph is positive. I can see that's really all I care about here. I don't want to find out where it's 0, positive, and negative. I only want to know where is this polynomial very specifically greater than 0, so where it's positive. So I want to find what x values cause my y coordinate to be something that's positive. Now, if I had, it depends on the question, if I had a calculator to describe this, I would actually graph the polynomial. on my calculator and then identify where it crosses the x-axis and look at it just like up here, find out what x values cause the y-coordinate to be positive. But let's say I don't give you a calculator. If I don't give you a calculator, then you're going to need to identify how to factor this. Our rational root theorem would say there are lots of possibilities. There are a lot of factors of 24. All those plus or minus being divided by 1 or 2 can all be possible rational solutions. Now I'll tell you that actually -2 is a place where the graph crosses the x-axis. So I know that x plus 2 is a factor. And so if x plus 2 is a factor, I know I can do a division. I'll do it synthetically to determine what the quotient is. And the quotient will end up being something that's a quadratic. And once we get quadratic, we can break anything down. So we've got 2, -11, 12, and you can see that the remainder is 0. So this polynomial does break down into x plus 2 times 2x squared minus 11x plus 12. And I want to know when this is greater than 0. And we just need to finish our factoring. And if I try 2x and x, and try a 3 and a 4, with both of them being negative, I get the appropriate middle term when I try to remultiply it out. Okay, now I have 3 factors that multiply together to give me this polynomial that I'm trying to analytically solve. And so I can do this a couple different ways at this point. One is to, again, identify the zeros and sketch the graph of the polynomial and try to find where this graph is actually positive. So if I do that little sketch up here, I know I have a 0 at -2. I know I have a 0 at 3/2 or 1.5. I know I have a 0 at 4. Now I can see that this would be a cubic function that has a positive lead coefficient, and I don't have any multiplicities on my 0, so I know my graph is doing something like this. Now I look back at my inequality. On my inequality, I need to determine where my graph is positive. I have to tell what x values cause my graph to be positive. I know that the zeros occur at -2, at 3/2, and at 4. So I can see that I will satisfy the condition for this inequality for it to be positive if x is between -2 and 3/2, or if x is greater than 4. So those are my solutions. Now I could also write that in interval notation if I so choose, and have -2 to 3/2 united with 4 to positive infinity. So that would be another way to show this. Now sometimes we have inequalities that the graph is not terribly nice as far as the zeros that it has. So if I gave you this question and it says solve graphically, I would start out with putting the inequality back into a set equal to 0 form. And I can see the similarity between this question and the question up above, that I have a cubic function with a positive lead coefficient. So it's going to resemble the graph very similar to number 2, where it's going to start at -infinity, possibly hit the x-axis 3 different times, possibly only once, maybe 2 times. It could be a double root. And we'll find out that if I try to use my rational root theorem here with utilizing the plus or minus 1 and 2 as my only possible rational roots, that none of them work. 1 and -1 are not zeros, 2 and -2 are not zeros. But this is being identified as having something that I want to have it graphically solved. So I would graph my equation. Go into my calculator, type in my equation. I have one that was in here previously. I'll just do some manipulation on this one. And I would start out with a standard window. These coefficients don't appear to be too bad. I would double check and make sure I don't have a mistake in inputting. Looks like it's okay. And I would go with a zoom standard, and I'll see what happens on my screen if I see enough of the characteristic of the graph to be able to describe. Okay, so I do. I can see the graph, and I can see that a little sketch here on my paper. I can see that the graph is coming up like this, coming down. And this time, I'm trying to identify when my graph is less than or equal to 0. So I want to give what x values cause my function to be less than or equal to 0. And I can see that's going to happen here, and it's going to happen here. So I have to identify those spots, which means I'm going to have to locate the zeros on my calculator. I'll find one. If I go to second and calculate, I can identify a 0. I need to get to the left of it, which I will do, and I'm going to get to the right of it. Don't want to get too far past, and then enter, and I have a guess, and leave it just in the same spot, and I find out that that 0 is taking place at 0.32 approximately. And I also went through and identified these others by using the same technique and found out this point is about 1.46, and this point is about 4.21. And then I'd be ready to graphically give my window. And so I have anytime x is less than or equal to, because I can have the equality of 0, 0.32, I have values that are negative. Or anytime I have my x value being sandwiched between 1.46 and 4.21, I also have values where the functional value is negative or equal to 0. If I gave it an interval notation, I could have my left parenthesis negative infinity to 0.32, close the bracket, united with 1.46 all the way up to 4.21, and close the bracket. And that would be in my interval notation.